Greetings, this is Cantaloupe Scott, and I'm here with a 5-part presentation on geometry, programming Platonic Solids via the Canvas API, HTML5. And I'm going to start with a tetrahedron, the simplest of the 5. And I have another video showing how to set up a responsive Canvas shim. If you want to review, that would be a good thing, or if you've already seen it, that's even better. And I'm going to flash forward through that real quick, and then while we're looking at that, we will discuss the geometry involved in a 3D solid. Now these are unique. The Platonic solids, there's only 5 of them, and the definition, the official definition is irregular polyhedron. That means each facet or face is identical, and all of the vertices, the points, the corners that is, circumscribe a sphere, a perfect sphere. So there's only 5 configurations of geometry that can achieve that, and they are the tetrahedron. It's a 4-sided, tetra means 4, a 4-sided shape, the cube, which is 6-sided, or a hexahedron, if you want to be technical, the octahedron, which is similar to a tetrahedron, but it has 8 sides, and it's like a double-sided pyramid, kind of. And you have the dodecahedron, which is, dodeca means 12, it's a 12-faced shape. And the icosahedron, which, as you may guess, is a 20-sided shape. And we'll finish with that one. That's the most fun, and I'm wishing I could start with that one, but it wouldn't be proper. So we'll start with the simple one. All right, we're set up with the shim now. Okay, I'm going to go ahead and review the tetrahedron math. All right, so getting into our main loop, which has also been covered previously, setting up the request animation frame call gives us a recursive animation loop that targets 60 frames per second. And this is just some basic boilerplate to get started. I'm going to add my rotation function, which I call R. Probably need a better name for it, but R works. And to review very quickly, it does 3 rotations per call along each of the axes of the standard 3D space, or Cartesian coordinates, whatever you want to call them. There's X, Y, and Z. So if you've seen graph paper, you have X and Y. It's basically a 2-dimensional space. If you add the Z component, that's depth. You have 3 dimensions. So each call to the R function will rotate by the degrees you provide the function about each of these axes. And it operates on a single vertex at a time, but it's in a loop, typically. I don't usually rotate a single vertex. It's an object that's being looped through, so each vertex in the object is passed through this function very quickly, and the effect is the whole object is rotated however you want. So the function is laid out now, and I'm going to begin the tetrahedron part, and we can just make that a function as well. It can be a modular function. It's called modular. If you can copy it into some other program or application and use it independently of this program, it's called being modular and compartmentalized, which is very it's encouraged, it's recommended in programming and software in general, because you never know if you're going to need a tool, or in fact there's a whole methodology called so I don't want to get into it, but it's called OOP, OOP, object-oriented programming, and it's all based around modularity and being able to reuse objects as prototypes. But I don't usually use that style. I use functional programming, which is just as valid. It's a different style, but you can still reuse code. So with that in mind, making a function out of this makes sense. So if I wanted to include it somewhere else, I could very easily. Okay, so I've defined 4 input parameters. Those are clearly size, and 3 variables called tx, ty, and tz. These are not actually used in this video or this demo because I don't need to. I'm making a single shape. It's not involved in a scene. It's not involved in a game. So you can probably imagine what they're for. They're for positioning, optionally, if you wanted to call this function and give it a default position in space. You could add those coordinates to the end result, whatever it is. And I just put it in there for in case I want to use it in the future, but I don't use it in this one. So I have a couple of arrays declared so far, one called ret, which is short for return value. I'm preparing to return an array or an object shape. I have one called a, which I typically use as a temporary holder. It's like a sort of a if I'm not finished with some data, I might stick it into something called A and then do some further processing on it. A is a very transient array, usually, for me, if I'm using the letter A. H is, okay, so H is interesting in this function. H, in my vernacular, could be just about anything, but it's the size that is provided to the function divided by an interesting number. And you may be familiar with the golden ratio. It's a magic number, and I think I'm using the gold. I should have checked this before the video. It's either square root of 2 or the golden ratio. I'd have to double check, and I will actually check that. But it's a magic number, and it's necessary to make the sides fit together. And you'll notice that I'm applying it to the size variable, so it just makes everything fit properly. And I did a little bit of calculation in the background to make that happen. And you'll see here what I'm doing is I'm plugging X, Y, and Z into the A array. You can push. There's a JavaScript function called push, and you can push a value or whatever onto an array. This is basically doing the same thing, but it's a shorthand way of doing it. It's called the expansion operator, I think, the ellipsis. If you prefix an array name with that, it expands it. So you can actually use this syntax that you see here with the ... A, comma, and then a smaller array with X, Y, and Z to just push onto the A array. And it's just a little shorter, and I prefer it because it looks nice. I don't know. There's no real performance difference, as far as I know. So, and then what I'm doing is, you may be familiar from my past videos where I generate data, some geometric data based on a loop and sine and cosine. So that's exactly what I'm doing here. I have a J loop, and the magic number you'll see is 3, which is a triangle from past videos again. So I'm drawing a triangle, and I have another point that is spaced above the triangle in 3-dimensional space, and then I'm basically just going from one side to the next. Remember, there's 4 sides, so there's a base, and I grab that first, put it into the array, and then I'm grabbing one side, and then rotating, grabbing the second side, and then the third side, and they're all going into this return array. And you'll see it's placed strategically in the loop to grab A, which is then cleared and repopulated. So it's a pretty fast, simple shape. I mean, you wouldn't expect a tetrahedron to take a long time to program. So I'm almost done here. And then finally, I know from experience making geometric shapes, especially Platonic solids, that it's advantageous to sometimes center them. especially the tetrahedron, because it doesn't come out centered by default. So what I'm doing is I'm grabbing the averages of each facet. So a vertex is three components, x, y, and z. A facet, in this case, is 3 vertices. And then if you just add the averages of x, y, and z, so you average x for a face, then y, then z, you get the center point of that face, regardless of its orientation, which is pretty interesting. You can do it for a whole object or a whole facet. What I'm doing here is I'm grabbing the average of all the center points of all the faces to get the center of the object, and then I'm adjusting the position of the output by that center point, so the object comes out centered. And we're just applying those averages to the return value before returning it. And then lastly, it'll need to be drawn. And this is kind of an interesting factoid about my style of animation. You may have a different style or know somebody with a different style, but all of my objects and models have kind of naturally fallen into a pattern where I use the same kind of depth and looping to draw them, which is handy because I don't have to really think about it or reinvent things on the fly anymore. And it starts with, I have an individual object and I loop through the faces because they have either quads or triangles or whatever. A begin path before that, draw the lines and or potentially fill the polygon at the end of that loop. And so it's always got a consistent and predictable structure to the shape, and it works pretty well, and you'll see that here. So I'm just doing a couple little fixes because I left a couple of things out. I left the Q function out and I had to re-add that. You can look at my previous videos for that explanation, what that function does. It's just a projection onto the screen. And then the globals OX, OY, and OZ, roll, pitch, and yaw, those are just the camera position and the orientation of the camera. So it's an orbit camera, and if you're familiar with 3JS or a lot of different types of geometric systems, you'll see the orbit camera is a common thing. You can just orbit around a point or an object, and that's all this does. So you'll see I'm calling the R function here to give it our camera orientation, which rotates every vertex in this shape, like I said. And you'll notice this is actually, I forgot to mention this in any previous video, after you call this function, the R function, it doesn't discern between what's in front of the camera versus what's behind the camera. And this is absolutely critical because what's behind the camera does not want to be drawn, or else it doesn't make sense on the screen. So it's real easy to check if Z is greater than 0 after you call the R function. And I'm used to typing it. In fact, there's probably a real easy way I could integrate that into the function directly. I don't want to limit the functions, and maybe I want to check something behind the camera. I've never needed to, but you never know. So I'm just used to typing the R function, and then if Z is greater than 0, do something, like draw a line or whatever. And here, I had forgotten to clear the screen, which is pretty important. If you're defining a fill style, it might just fill the whole screen with a certain color, and maybe that's not what you want. So getting real close to being done. Again, the closed path on a 3D shape, it's not super critical, but you may actually notice that one of the sides, especially if you're dealing with two polygons that are joined with an edge, that edge on both polygons happens to not be closed, you're going to notice that one of the lines isn't being drawn if you're drawing the lines versus just filling the polygons. So you want a closed path usually. I have described it in a lot of previous videos. It's part of the API, and it just finishes your polygon. And this is something here, this last little bug that I'm working on. I fix it in about 30 seconds, but I have consistently forgotten to assign the width and height of the canvas on the inside. Now, this may be a little confusing because you have two sets of dimensions for a canvas. You have an external and an internal. So the external is what is concerned by the browser. The element has a width and a height, but the environment inside the canvas is completely independent of that. It can be much, much larger, much, much smaller. So when you set the canvas element width in JavaScript, you're describing the inside of the canvas, and I just now added that, and you'll see it's the correct shape all of a sudden. The screen was red previously because it was the wrong size and the shape was taking up the whole screen. So if you notice that things are the wrong size, maybe make sure that you have set your dimensions properly. So here we have it. That is the finished tetrahedron there. I'm just doing a couple little things with the rotation, and it looks good. I think that's about it. So I'm going to move on to the next one, which is a cube, and that one's even easier. So thank you for joining me, and I hope that was illustrative, and have a great day. Thank you.